Thanks. So first, thank you for your great hospitality and having me here today. After seeing your facilities, and I'm very impressed, and actually it's made me a little bit nervous now to see such great work. So the title of my talk today is Electrical and Optical Properties of Defects in Ion Implanted Silicon. This is very broad because title because I wanted to just describe a few of our projects that we have at Melbourne. Hopefully it's not too shallow and superficial, because there's about 4 projects I want to discuss, but hopefully we can maybe discuss certain aspects a bit more later on. So just to put myself in context, these are some of my collaborators. At University of Melbourne, my bosses Jeffrey McCallum and David Jamison. Nick came here, as you mentioned, and he's now working with us doing some PL measurements, which I'll talk about a little bit. We also have, under the Center for Quantum Computing, we have a strong collaboration with UNSW. So you may be familiar with Andrea Morello's work and Andrew Zurek. I mostly work with Lawrence, who does a lot of the ADMR type experiments, and I'll talk a little bit about what we do, the next generation of devices that we're working on. Other than that, I do a lot of ion implantation type physics. So with that work, we collaborate a lot with Jim Williams, who's in Canberra, which is Australia's capital. And Jenny Wong Luang, and SuperKit. We do a lot of PL with them as well. And we just started working with Purcell. You probably yeah. So we're speaking to him a lot about crystal trim. So I'll present some of those results as well. I guess so. As a semiconductor physicist, the main motivations can be described well by Moore's law, as you know. So this is my Moore's law type picture. This is the Atari I used to have when I was little, and during that time, the technology node was 2 microns. But now on this, my funky Mac, it's at 65 nanometers, and it's good to see that you guys are using Macs as well. So very cool. But of course, things are getting smaller, and the functionality is increasing. So eventually, we're going to reach some fundamental limits, and that requires us either to do one of 2 things: either refine our current knowledge, or otherwise try to search for novel devices, including the quantum computer type devices. So in computers like this, ion implantation is a popular technology to fabricate devices. So this is just a graph of all the different types of ion implantation you might use to fabricate a device. For a standard device now, I think there's about 40 different implantations to fabricate a chip. So for example, you might do some channel engineering in a MOSFET. You would do arsenic or phosphorus implantation into a channel at these sort of energies and these sort of fluences. And ion implantation has been used for perhaps 50 years now, so it's a really well-developed technology, and it has excellent control over placing a dopant or an implanted species where you want to. So at Melbourne, we use ion implantation partly to try and fabricate our quantum computers. So we're mainly looking at the phosphorus in silicon system. So this is a schematic of the type of single ion implantation technology that we've developed. So we have our substrate chip where we want to make our device, but it's also got a PIN type detector incorporated into the design. So when we implant just one phosphorus ion, we will get a signal in from the electron hole pairs that are generated during the implantation. So then we know that we've implanted just one ion, and so this is moving towards this type of either a Kane quantum computer or this charge-based quantum computer. So some of the devices that have come out of the center have been some silicon quantum dots, and the spin-dependent transport devices. That's a ADMR, which I'll talk about later. Other than, so this is the colutron, by the way, that we use for the phosphorus implantation. This is quite small. It's probably about from here to the wall, and it's optimized just to do the 14 keV phosphorus. So other than that implanter, we have access to the ion implanters in Canberra at Australian National University. So they have a tandem accelerator there, and a smaller accelerator. And in Melbourne University, we have a Pelletron type accelerator. So you can't see it, but just at the top here, there's a big tank, which is like a Van de Graaff machine, and that can accelerate protons or helium atoms. And that comes down around a 90-degree magnet here, and down one of 3 different lines, beam lines that we have. So this is our microprobe beamline. We have a spot size at the chamber of under a micron, and we use this to for various techniques. We can do implantation with it, but we also do a lot of Rutherford backscattering spectrometry, and we look at the charge collection efficiencies of our devices as well. So the bad thing about implantation, of course, is that it causes damage. So, for example, you have an implanted ion into your lattice here, and it might knock out a silicon self-interstitial. This is a defect, and you have interstitial dopants, and then we'll leave a vacancy there as well. So vacancies and interstitials are, as you know, both mobile at room temperature. So sometimes they might recombine, or they'll form more complicated structures. After implantation of a dopant, we usually do an anneal to activate the dopant, which means put it onto a substitutional lattice site. So the types of defects that we try and anneal out might be these point type defects. So, for example, the W center, which is a cluster of 3 interstitial silicon atoms, which I'll speak about later. Or you might have vacancy-related defects, like divacancies. So after anneal, under some conditions, you might form these dislocation loops as well. But then if the fluence is greater, you might get a phase change into amorphous silicon. So in this talk, I want to just talk about these 4 very different projects that we're doing. Most of my work has been in amorphous silicon, actually. So I'd like to show off that work. But there's these 3 new projects which I thought would be very interesting for you, as they are for us. This is channeled implantation, photoluminescence of implanted silicon, and the ADMR devices. So first of all, solid phase epitaxy. I actually spoke about this at the EMRS conference, so it's okay if you fall asleep or something since you've seen this before. So if you're making a shallow junction, you have to use KEV implantation, so the dopant is very shallow, so it's likely that you form amorphous silicon in the near surface. So then you would use some thermal treatment, say above 500 degrees, to activate the dopants and to recrystallize this. And this has been identified as being the most promising way to activate dopants with a low thermal budget. So it's a popular technique. So what it is pretty much is the transition between amorphous silicon to crystalline silicon. So you have an implanted dopant here, and this you have an interface between the two. And as you heat it up, this interface moves towards the surface, just layer by atomic layer. And we can measure the velocity of this interface with a reflectometry system, because laser light will reflect off the surface as well as the interface. So we'll get these squiggly lines here, and we can work out the velocity. So the solid phase epitaxy velocity has a lot of different dependencies: temperature, pressure, crystal direction, and the dopant concentration. It's a thermally activated process, and it's described by an Arrhenius type equation, has an activation energy, which is 2.7 for silicon, and germanium we published 2 years ago now, is 2.15. So as I said, it's also dependent on the dopant concentration. So for example, if you have arsenic in the amorphous region, then this is the velocity versus the depth. The red ones are enhanced. The SBE rate speeds up as it goes through the arsenic profile. And the same occurs for aluminium, which is a p-type dopant. But if you have both of them in there at the same time, then you'll get a compensation type effect. So that's the green line. And the enhancement is cancelled. So this suggests that it's dependent on the Fermi level. And so we've developed a generalized Fermi level shifting model to describe the process. So what it is pretty much is we first off start by saying that the SBE rate is dependent on the concentration of some sort of defect. We don't identify that defect. We just think that it's some defect which aids the bond breaking and rearrangement at the interface. Then, using Fermi-Dirac statistics, we can see that the charge state of the defect is given by this, where G is its degeneracy and E is the energy level. So, for example, if you change the temperature, going to lower temperatures, which is this direction, the Fermi level shifts towards the dopant band. And so you can see with this equation, as that occurs, the charge defect concentration increases. And we see this characteristic effect in the velocity as well, the normalized velocity. So at the lowest temperatures, you get the greatest enhancement of the velocity. So this is the type of equation that we use to fit the data. G and E is the free parameters, so we can use those to try to identify the type of defect that we're looking at. So we did this for arsenic, phosphorus, boron, and aluminium. And we saw, there's a lot of information here, sorry. But we saw the same sort of effects for each dopant, except for aluminium. Aluminium's a strange dopant. We think we see a kind of decrease here, but this is probably because aluminium forms a silicide at the interface as you recrystallize. So probably if you implant an aluminium profile, it might shift around a bit as you use solid phase epitaxy. So aluminium is a bit frustrating. So if you're looking at the band diagram here, I've just pointed out some of the known defect levels. And so we've identified these defect levels here for each dopant type. So that we see a realistic sort of data, but it really requires another type of experiment to pin down what that defect actually is. So we've been looking at other systems as well. So you might have noticed where there's no dopants here, coming back to this graph, you see a decrease in the SPE rate, and this is because hydrogen is indiffusing into the sample. And I have an animation here, but it's not going to work. So I'll try and describe what happens. It's just like a error function, and the hydrogen diffuses in, but from this end, the interface is coming towards the surface. And as that occurs, the hydrogen segregates at the interface, and it gets pushed back out of the sample. So we became interested in the hydrogen diffusion because its activation energy is the same as the SPE process. So this suggests that hydrogen diffusion and solid phase epitaxy are related somehow. Perhaps they're the same defect, the same mechanism is operative in both processes. So I have here, this is what really motivated us to start looking at diffusion studies, just in not isotropically pure or anything, so maybe one day. Have here just the hydrogen concentration after a low temperature anneal for 90 minutes. And you can see for intrinsic, you will just get this normal error function type trend with segregation at the interface. The interface, this is all amorphous, and then the interface is 1.2 microns, and then beyond that is crystalline silicon. But if you have phosphorus or boron in the near surface layer, which is a situation you might meet when making a shallow junction, then we find that the hydrogen concentration is increased. I had an animation there, but it doesn't work. So this is just some of the data that we were able to publish last year, just recently, I think, probably a couple of months ago that came out. So as an unannealed sample is the dashed line just here, but after 500 degrees for 5 minutes, without any dopants, there's just a slight decrease in the peak and a broadening. But if you have boron in there, which is this profile here, this is formed by ion implantation, and you can see the broadening is much greater. And so this is boron-enhanced hydrogen diffusion. And we tried to do this for many different temperatures. And we found that it was thermally activated over the temperature range that we studied. There was no time dependence that we could find. And you can see the normalized diffusion coefficient that we found was enhanced for the lowest temperatures. Again, the same as in the solid phase epitaxy velocity case. So this is extra evidence that these two processes are linked somehow. But the model, when we applied it to hydrogen diffusion, came out with very different numbers here. A little bit unrealistic, plus or minus -1 here. But we sort of expect there to be differences because there's two different materials, and we measured the Fermi levels we had to calculate the Fermi levels in crystalline silicon and amorphous silicon. But actually, so a lot is known about silicon, but in amorphous silicon, it's like the dark side of the interface. There's not much known about it, so it's a bit tricky to calculate that one. For example, the effective mass isn't known that well as the band gap narrowing. But anyway, it's a good phenomenological model for both SB and hydrogen diffusion. So that was that work that I wanted to show off a little bit. But now I'll just briefly speak about a few other projects that we have. So this is the channeling implantation that we do a little bit with Pussalt in Germany. So I'll talk about the simulation of implantation, the techniques we use to measure it, and then some of our recent results. So usually when you do an implantation, you might simulate it with SHRM. You can download this off the internet. It's free and fairly easy to use. It will give you the projected range of your implanted ion. I think this is 450 keV phosphorus. It also gives you the vacancy profile and the energy loss as well. But the bad thing about it is that it assumes the target is amorphous, so there's no crystal direction. So you can't simulate channeled implantation. But that's where crystal trim, which Pussalt developed, takes over. So it's also part of TCAD. I think the DIOS package in TCAD has crystal trim incorporated into it. So this is the phosphorus concentration and the vacancy profiles for both random and channel directions. And you can see there's obvious differences between the profiles there. So we were perhaps initially interested in channeling because the fluence or the damage created is much less than in the random direction. So you're creating less defects, and so that was our initial motivation, as well as to test crystal trim, which actually hasn't been tested as extensively as SHRM. So to characterize these damage profiles, we use DLTS, deep level transient spectroscopy. We have 2 or 3 systems to do the measurements. DLTS works in a number of different modes. Here's our sample stage here. It's really sensitive to low defect concentrations, so you can do these experiments without amorphizing the sample, and probably you couldn't use SIMS to measure the phosphorus profiles here. It's because it's such a low concentration. So in the past, SIMS has been used to test crystal trim, but the defects form would cause dechanneling, so really it's not a true channeling experiment. So basically, just to describe the technique, if you're not familiar with it, we have a Schottky diode here that's biased up, which causes a depletion region here. We pulse it to bring the electrons up to the surface. It fills these traps, and when we pulse it back down, the traps emit electrons, so causing a capacitance transient. So we're interested in this transient here, and from that transient, which is described by this equation, we can work out the both the emission rate and the concentration of traps. For this work, we use a double boxcar method. So we just take the time at 2 points as a function of temperature. So temperature increases, the emission rate increases. So if you take the difference between these 2 points in capacitance, you'll get a peak. And then with this peak, you can relate to the concentration of defects here. So this is some data that we have from 80K up to room temperature. We see maybe 4 peaks here, which all correspond to different types of defects. So vacancy oxygen, which has this energy level below the conduction band, which gives this peak up to, say, a vacancy phosphorus, which is a lot deeper into the band structure. So if we sit at this temperature, we can use this double correlation method to do a depth profile of this trap. So basically it's the same as DLTS, but we have 2 pulses now with slightly different peak heights, and we shift those through the substrate and can get a depth profile. So we've compared these profiles here to the simulations. Of course, you can see that the concentration decreases as you would expect as you go to the channeling direction. So this is the data compared to the simulation. So you can see it's really a bad comparison. It doesn't match at all, but this might be expected because dynamic annealing effects. When you implant the ion, the vacancies and interstitials will recombine, so concentration is a lot smaller. But if we rescale it by 70 times, for example, for the random direction, we see that the correspondence is quite good. It's not so good for the slightly off-channeled one, but the channeling profile compares quite well. So we're pretty happy with this result. We also looked at hydrogen implantation at 70 keV. So this is where it became a little bit more interesting. Again, we see this kind of discrepancy, and then the rescaling. But you'll notice that the simulation has this characteristic peak, as we saw for the phosphorus, but for the hydrogen, we never saw like a similar similar channeling tail. Also for so in the simulation, you can give your beam a divergence. Say that there's a 1% error. The experimentally determined value was 0.36 actually. So, but we could never get the simulation to match experiment here. The simulation couldn't be adjusted realistically, unfortunately. So this is a little bit of a mystery to us. We also looked at helium, another light ion, and we found that this effect was much more pronounced. Again, you see the channel, but not in the data. So again, we couldn't adjust the simulation in any way to fit the data for the light ions. For phosphorus, it worked really well, and but for the low ions, low mass ions, we couldn't see this deep channel, and we speculate at this point that this could be because of a dynamic annealing effect. So when you implant phosphorus, for example, the vacancy profile overlaps the interstitial profile. But if you implant a low mass ion, then the interstitial profile will be a lot deeper than the vacancy profile. There will be a greater offset. So if there's any recombination occurring, then it's more likely that the recombination would occur in the tail of the implanted vacancy profile. And so this is why we suspect that it's some dynamic annealing effect. Next, we want to look at boron, which is not a light ion, and see if we get the same sort of an effect. Boron, of course, is technologically important type defect, so that'll be exciting. I hope I am not going too much over time.
That's fine.
Okay, I'll keep on going then. So we do a lot of photoluminescence as well. And so I'll just briefly speak about the PL in silicon and interstitial related luminescence centers that we've been looking at recently. Generally, for room temperature photoluminescence, silicon is really annoying to work with because it's an indirect band gap. It's difficult to get light out of it. But it's usually phonon-assisted photoluminescence. But if you distort the lattice by introducing dopants or defects, you might get a direct band transition. I think this paper came out 2004, which showed room temperature luminescence through dislocations. These were formed by compressing the silicon to form slip dislocations. So for a LED, this might be a promising way to incorporate miniature lasers onto integrated circuits and have everything made of silicon. So we've actually looked at what's known as the W line. It's now known that it's now supposed that it's a 3 interstitial cluster. This was determined by its behavior under pressure. There's also an X center, which is a 4 interstitial cluster, and the Y center, which is similar to the W center, but it has boron in it as well. So you have this zero phonon line as well as the phonon replicas. We can see that 80K on our spectrometer, but it thermally quenches. You can't see this at room temperature. But an LED has been made with the W line recently. To make the W line, to make the center, all that's required is some damage in the lattice. So you might do that with electron beams, but we've done it with silicon implantation. And then it's a low temperature anneal. So it's a small defect. It's not very stable. It just requires 270 degree anneal to form it. So for higher anneals, then it disappears. More complicated structures are formed. So for example, the W center is thought to be a precursor to dislocations. So a W center becomes a 311 type defect with higher temperature anneals. So we've maximized the luminescence here at 275 degrees. My slides are a bit mixed up, but this is the motivation for our work. This is the Optics Express LED demonstration of a W-line electroluminescence. The W-line probably in this device wasn't optimized, and they observed some issues with boron doping. So we looked at that in a little bit more detail. So we had 3 different substrates which had different boron concentrations. One was 9e to the 14, 1e17, and 3e18, quite high boron dopant. We formed the W center in each sample, and for the low boron density sample, we saw the W line. But as the boron concentration increased, the W line decreased in intensity. And we found that as well for the 400 degree sample. So we've just submitted this a few weeks ago to APL. The reason that this occurs, we think it could be two possible reasons. The boron, in this case, forms boron clusters, and these clusters act as non-radiative pathways. So it becomes more likely that the electrons recombine through these. Or otherwise, the actual formation of the W center is suppressed by the boron, because boron is known to soak up interstitials. There's been some theoretical modeling by Pelaz in Spain with the boron interstitial clustering. So actually, in a higher temperature regime, there's a similar effect for the formation of 311 defects. So if you have a high boron concentration, you can see the dislocations start to disappear. So we think there's a similar mechanism operative here. Yeah, so there was no W lines observed for this threshold type concentration. This range is a lot less than that which prevents 311 defects, which is 1E19. It's quite close, but an order of magnitude. For higher temperature anneals, the boron clusters emit interstitials, so this could explain this discrepancy here. So we're going to keep on going with this work, and we'll also look at the dislocations formed by ion implantation. So that should be exciting. So lastly, probably you'll be most interested in this, the ADMR type experiments. So for the quantum computer, of course, the information is held in a single spin, but the challenge is the control and readout of that spin. I should change this now because I saw some new measurements which I think increased this number by Professor Ito. So anyway, this is an attractive system because of the long coherence time, which is limited by the silicon-29 concentration, and this can be decreased by processing, as you well know. So this is a schematic of an idea developed by Morello, who came here recently. I think this is on the archives. I think it might be coming out in APL soon. I'm not quite sure. So basically, I'll just describe what happens here. It's a spin-to-charge conversion type device for quantum computing. You have your MOSFET down the bottom here with your source and drain. You have the two plunger gates, barrier gates, which form a silicon quantum dot in the middle. But then over here, it incorporates this ADMR type structure, which is just another MOSFET gate, but you have a single phosphorus ion underneath that gate. So this gate controls the spin of the phosphorus, and then depending on the spin state of the phosphorus, this is, by the way, the band diagram going along this dotted line through the single phosphorus, where you get this dip, and then through the quantum dot to the drain. So you'll get an SET island here, and then you would get a spin-dependent transport with the SET. So when the charge moves, there's a change in the electrostatic force, and you can, if you see a change, then you know which spin state your phosphorus atom was in. Excellent. So I'll just talk, for the rest of the talk, I'll just talk briefly about some fabrication ideas we have on this part of the device. So this initially came out in 2008 by Laurens, this type of ADMR device. Sort of innovation with this is that the gate carries the RF field as well. So the RF is just exciting spins in the channel locally. So only spins within the channel are resonated with the RF field. So it has, for this initial device was this phosphorus concentration here, 80 to the 16. The source and drain leads were phosphorus indiffused, and there was a 20 nanometer oxide on top of that. So the ADMR signals that you would see with this device, this is just the source drain current. You see the drop here, but if you're looking at just the delta I over I, then you'll see the this middle feature, which is due to the resonance of the 2-deg and the hyperfine resonances of the phosphorus as well. So these are two different techniques that were done on the same system, magnetic field modulation and frequency modulation. This is 16 sweeps to get good enough statistics here, and just 4 sweeps here. But actually recently, I don't have the, I think, yeah, this is the reference here. So we can now do single shots by using this, a new circuitry which Laurens has developed, looking at the reflectance of the RF signal. So this paper has the block diagrams and everything of that circuit. So part of what I've been looking at is trying to make this device with ion implantation, which has been a little bit tricky. First of all, we were worried initially that the some of the phosphorus in the source drain leads was resonating as well. So we wanted to put arsenic into the channel instead of phosphorus to just to confirm that we weren't seeing any non-local phosphorus effects. So probably up to a concentration of 1E18, you would be getting resonance, but above that, you don't see the hyperfine structure. So this is the original device. We've already tried this device here where the phosphorus leads were indiffused, but I implanted arsenic into the channel, which gives this type of profile. But actually we used an epi layer here which had a high concentration of acceptors in it, so that quenched the hyperfine lines. So that was a little bit annoying, but we were able to optimize at least by looking at the defects created here, minimizing those, and came up with this fabrication process. So we use an RTA annealer after the arsenic implantation. So the reason we do implantation through the oxide, that can be, is because if you grow the oxide after the implantation, you have to heat up your sample to 900 degrees for 40 minutes or something, so the phosphorus will diffuse around. So we're trying to avoid that. You might use a low temperature oxide growth technique, which I think has been done at around 300 degrees now, but it's quite specialized and difficult to perform. So we do the implantation through the oxide itself. And so the measurements that we've done to look at the defects is DLTS again. you cause different sorts of defects in your substrate. We're most interested in the interface traps here. So these can also cause decoherence in your phosphorus atom. So when you use DLTS, you're pretty much looking at the density of interface states at the silicon oxide silicon interface. So you'll see this characteristic U-type spectrum. This is just looking at the top half of the band gap. In this experiment, we actually found that implantation improved the oxide quality. We think, so this is the Asgreen spectrum. The density of states is around 1E11. This is quite high. This is too high to do for a quantum computer. There's too many defect states at the interface here. But after implantation and plus an RTA up here, all of the concentrations drop down. And it's been our goal to get this down to 1E10. And this is the start of last year, start of 2008, presented at MRS. But we're now up to 1E10, so we can produce high quality oxides, which are down at this level now. So this is an interesting result. We think it's because the implantation relaxes the bonds at the interface, perhaps, and in that case, they can reform and form a lower defect density. So one of the next experiments that we're going to do with the ADMR device is use it as a spectroscopic tool to look at how phosphorus, the ADMR changes with the distance from the surface. And we can also perhaps control the number of defects at the interface as well to see what effect that will have on the phosphorus. We're also going to make a ADMR Hall bar type MOSFET device so that we can do mobility measurements at the same time with exactly the same device. So actually, I think that's all. Just to summarize, said that SBE, the crystal trim, boron effects in the W-line formation, and the ADMR experiments. I hope you've found it interesting. Thanks.